Hey everyone, it's Mr. Canfield. We're gonna do some BC calculus today. So this is the improper integrals and some other stuff assignment that I gave you guys. So I'm gonna walk through this. Hopefully it's helpful. Let me know if you need anything more than this. So this first example doesn't even look like it's an improper integral, but if we realize when we plug in 0, that's allowed. But -3 here is going to be a discontinuity. And so because of that, we're going to have to take the limit as b approaches, I almost wrote negative infinity, -3 from b to 0 of 4 over, I'm not going to write 4 over, I'm going to write 4 times x plus 3 and rewrite this as an exponent, because that's how you're going to figure this out, what the antiderivative of this is. So it's the square root of this cubed. So square root means 2 goes on the bottom, cubed means 3 goes on the top, and it's under here, so it's a -3/2. And so I figured all those pieces out. So now if I'm going to do, why am I writing on this paper? Whatever, I'll write the other ones on a different piece of paper because I'm going to run out of room real fast. So now we'll integrate. We'll leave the 4 here. X plus 3, since its derivative is 1, we don't really need to worry about that. We can just treat this as if it was x to the -3/2. So we'll add 1 to the -3/2 and get -1/2. And then divide by our new exponent. So I just do it like that, keep life simple, and we're evaluating from b to 0, and the limit thing, as the limit, b goes to -3. So you got -8, x plus 3 to the -1/2, which we could rewrite, that as -8 over the square root of x plus 3 from b to 0. So when I plug stuff in, I get -8 over square root of 0 plus 3 minus -8 over square root of b plus 3. So if I do that, I get, oh wait, I made a dumb, we can't go to, we're not going from both sides, we're just going we're just going towards it from the right, so we only want 3 from the right hand side. And that's my bad. Okay, so all right, let's see what we get. I get -8 over root 3, and then I get plus 8 over root . -3 from the right plus 3. Wait, hold on. This bottom here is going to 0. This is -8 over root 3 plus 8 over 0. So we're approaching 0, which means we're approaching infinity. This is plus infinity. This is divergent. There's no answer here. So I think I could have ignored the positive side there and it still would have, like, well, no, because that's, yeah, whatever. I'm overthinking it. Yeah, okay. So, and with the height of quality, I'm going to move on to the next problem, and I forgot to bring scrap paper with me. So, let's see what I can steal from my belongings. There we go, okay. B. The integral from 1 to infinity of x e to the -4x dx. Okay, we got two choices. When I see this kind of thing, like, is this u substitution or is it parts? And so that's the kind of thing you're gonna have to figure out. This is u substitute, nope, sorry. The derivative of the exponent here is not the number up front. It's not u subs, it's parts. Let's make sure I write them in the right order. So u would be x, du would be 1 dx, dv would be e to the negative forks, v would be the integral of that, nice and easy, which is -1/4 e to the negative forks. So the integral of this is going to be -1/4 x e to the negative forks. Remember, it's uv minus the integral of v du. V's got a negative in there, so it's going to be double negatives. So v du. Oh, that's nice and easy. So, and then we're going to evaluate this from 1 to infinity. So -1/4 x e to the negative 4x. This integral, if I pull the quarter out, it's just -1/4, right? So that's going to be another -1/4 out front. What's 1/4 times -1/4? -1/16. E to the negative 4x, evaluated from 1 to infinity. Okay. So, and remember, we're taking the limit as b approaches infinity. I see we're going to run into a problem, so I'm going to change that and use b. So that's -1/4 b e to the negative 4b minus 1/16. That's a weird way to write 1/16 e to the negative 4b. Then minus -1/4 times 1 times e to the negative 4 minus 1/16 e to the negative 4. All right, let's, I might not need to do this. If this winds up being infinite, then I'm done. I don't have to do anything. So let's see. I get b is going to be on top here. This is going to be on the bottom. I'm going to rewrite this fraction to kind of think about it better, because this is infinity times 0, which is going to be a problem. Negative b/4 e to the 4b. And we're getting infinity over infinity here when we do this. So we'll need to L'Hopital's rule it. And you guys kind of bugged me in class, like, but I see this is going to 0. Do I really need to do L'Hopital's rule? If you can see that and you are convinced, no, you don't have to. You can go, oh, when I L'Hopital's it, the top will be 1, the bottom will be still a function that I plug in infinity to. Yeah, we're good. So this is going to 0. But to just kind of prove that, I get infinity over infinity when I plug this in, when I plug in infinity. And so if I take the derivative of the top, I get -1. The derivative of the bottom, I get 16e to the 4b. And now when I plug in infinity, I get 1/infinity, or -1/infinity, which counts as 0. So yes, I get 0 minus, oh, same thing here, right? 1/16e to the 4b. We plug in infinity there. This is going to go to 0 as well. This is all just 0. So I do need to figure out this piece. Minus, let's see, we got -1/4 e to the 4th. This we have 1/16e to the 4th. Distribute the negative and get 1/4 e to the 4th plus 1/16e to the 4th. So to get these together, I'm going to use a common denominator because I want to get them both to be 16. So I'll use 4 and 4. So 4 times 1 is 4, plus 1 is 5/16e to the 4th. And I am going to go check my answer with AP Classroom because I do not trust myself to do these. Oh, they just left it. They just left it here. They just left it here. We could have left it there. I'm so dumb. Why did I do all that? You could have said negative parentheses that. I'm fine. But hey, that's what I got. I got that for my answer. All right, cool. I just tried to put the marker cap on my pen. All right, number C. So C says 2 to infinity of 4 over x squared plus 4x plus 3 dx. All right. I'm gonna have to use partial fractions. Let's see. So let me figure this out. I'll remind you how we do this. So I factored the top because I'm a genius. And then I just said the top. Yes, I'm so smart. If anyone is actually watching this, I hope you're doing well, and I hope things are going well for you. Clearly, I am not doing great at math. All right, or words. Okay, so x plus 3. Well, plug that in first, and remember, we're plugging in the 0 of it, so I'm going to plug in -3 to the rest of it. So the 4 and the x plus 1, and that's what the top here is going to be. So let's see, -3 plus 1 is -2. So this is 4 divided by -2, I get -2, so -2 goes on top there. And then we'll plug in -1 to this guy and do that to what we see. So I get 4 over 2, and as we often get, we get the same number twice, 1 plus 1 minus, or something like that. So now I can do these integrals separately and get -2 natural log of x plus 3 plus 2 natural log x plus 1 evaluated from 2 to infinity. And we need to be careful because at the outset, you might be like, oh, excuse me. Oh, this is open and shut. They're both going to be infinite. But since this is a negative, I'm going to pull a 2 out front of both of them, right? If I pull a 2 out front of both of them, I can do that. And I'll say natural log, and now I can write this as a division problem because I have a negative. This is negative, so I can put this on the bottom. And this is positive, so I can put this on top from 2 to infinity. And so now when we do this and we take the limit as b goes to infinity, we get 2 natural log b plus 1 over b plus 3 minus 2 natural log 2 plus 1 over 2 plus 3. Well, let's look and see. When b goes to infinity, we get infinity over infinity. And so you got to do L'Hopital's rule. But if you do, you get 1 over 1 when you take the derivative of the b plus 1 and the b plus 3. So this is going to 1. So that's 2 natural log of 1 minus 2 natural log of 3/5. Natural log of 1 is 0. This goes to 0. And so my answer, you can do more algebra here to clean this up, but I'm just going to double check that all right, yeah. So they stopped here. You can do more. You could bring in that -2 as an exponent if you want to be fancy. And you could say natural log of 3 over 5 to the -2. So that would reciprocal it. So it's natural log of 5/3 squared. You could square both parts. Natural log of 25/9. And then for whatever reason, if you really wanted to, you'd be like, natural log of 25 minus natural log of 9. Like, all of these are the exact same thing as that, but why would you do that? You just leave it like that. I'm so funny. I don't know why that's funny. Okay, all right. Cool. Sorry for all the sniffling. It's fall. All right, number 2. The integral of 0 to 4, 1 over root x, 1 plus root x, dx. Okay. So, oh my gosh, that's awful. I'm so sorry. Okay, I see ln's here, and that's a hint to me about how I'm going to end up doing this. But I think I might be doing u substitution here. The reason I'm thinking u substitution is the derivative of the square root of x is like 1 over 2 the square root of x. And I see a 1 over square root of x here. So that would be a pretty cute substitution if I said u is equal to 1 plus square root of x. I could say du is equal to 1 over 2 root x dx. And so the 1 over 2 I don't see here, so I could multiply both sides by 2 and say this is 2 du is equal to 1 over root x dx. And so now I can replace this, and I could say, oh, I need to talk about the bounds. Give me a minute. So 2 du is equal to that. So I'm going to put a 2 du, and then I just have 1 over u. Well, that's pretty sweet. So the bounds used to be x. I remember that u and your x don't mix, so I would need to replace these with bounds that make sense in u. So if I plug 0 in for x here, then I get u equals 1 minus the square root of 0, so u is equal to 1. So my lower bound is 1, and my upper bound is when x is 4, I get, sorry, 1 plus root, sorry, I was just thinking about where I'm going with this, and I'm like, am I doing something stupid? So from 1 to 3 du, can I just do this? So here's the problem. This function is actually undefined when x is 0. We have 1 over 0. That's not allowed. So this 1 isn't technically allowed, but I'm taking the limit as x approaches 1 and just kind of doing it anyway. And then I'll go double check with College Board and see if I broke the rules. So this is, secretly, this is a limit. Let me just make sure I'm not super far off. Okay. So when I do this, I get 2 ln u evaluated from 1 to 3. The cool thing is if you do it this way, you don't have to go and plug in the square root stuff again. You can just leave it as u. 2 natural log of 3 minus 2 natural log of 1. Hey, what's natural log of 1? It's 0. So the answer for this is 2 natural log of 3. This is technically an improper integral, though, because the function is undefined as 0. Weird. Weird. Answer. That's the right answer. Oh, hey, there it is. Okay. Let's look at our next one. Number 3. So we'll go from 0 to infinity of x over 1 plus x squared dx. I'm thinking u substitution, because what's the derivative of x squared? It's 2x. I have a plain x up here. I think we're doing u sub. Let's set u equal to 1 plus x squared. The other thing that's nice is like a 1 plus x squared, u substitution kills that 1, and it makes it so there's a lot less to think about. But I'm just making it the inside. The reason I'm not making it the whole thing is the derivative of 1 plus x squared squared is 2 times the inside to the 1, then times the derivative of the inside, and that I don't see in my exponent. I mean, my numerator. So I might have picked this if I saw something like this as my numerator. So our du, nice and easy, is 2x dx. So we have x dx, but we need to get rid of the 2, so we'll divide by 2. So I got the 1/2 out front, and this time it's not 1 over u. This time it's 1 over u squared du. And we need to figure out our bounds. So if I plug in 0 here, I get u and 0, so u is equal to 1 plus 0 squared, so u is equal to 1 there. If I get infinity, then we still have infinity here, right? Because 1 plus infinity squared is still infinity, so we're just doing from 1 to infinity now. Is this undefined at 0? No, the bottom's 1, we're good. So this whole thing is fine. So now when I am integrating this, oh, well, that's not a bad integral at all, right? 1/2 is, remember, this is u to the -2. So we're going to add 1 to the exponent and then divide by the new exponent. So now we'll go from 1 to infinity of that. And I already have the 1/2 still there. Okay. So when we do that, that's the same as 1 over 2u evaluated from 1 to infinity. So I'll plug stuff in now. So -1 over 2 times infinity minus -1 over 2. So here, those will cancel each other out. We got a plus 1/2. This is 0, so our answer should be 1/2 if I am correct. I see 1/2 as an answer choice. It's the right one! Yay! Thanks, College Board. Okay. Let's keep going. All right. Number 4. An antiderivative of e to the x over e to the x minus 1 is the natural log of e to the x minus 1. Don't worry too much about that. Just know that if I take this derivative, I get that. Like, you don't need to figure out how it happened. They're telling you, hey, here's the integral. Which of the following statements about this integral is true? Let's see. So -2 to 2, e to the x over e to the x minus 1 dx. Well, one of the things that's really important with this is if there's an undefined piece along the way, you have to include it. So, for example, when x is equal to 0, we get 1 on the top, we get 0 on the bottom. We have 1 over 0. That is infinity. That means at 0, I need to break this up, and I need to look at these separately. -2 to 0 plus 0 to 2. So this is one of the key things with improper integrals. If there's ever a discontinuity somewhere in the middle of the problem, we need to make sure that we're breaking this up into 2 separate integrals. So I'm not gonna lie, most of the time that this happens, it just doesn't work. So, one of our choices is, here's our integral. And if we just plug it in and don't think about it, we can be like, well, the zeros aren't going to matter. They're going to kind of cancel each other out. But the fact that we get e to the 0 over e to the 0 minus 1 when we plug in 0 here, minus e to the -2 over e to the -2 minus 1. The fact that this is infinity minus a number, this side does not exist. And so oh, I'm dumb. That's not what I'm doing. Hold the phone. We need to use the integral they gave us. I messed up. I meant to write the integral, the ln of e to the x minus 1. So they said the integral of that was ln e to the x minus 1. So we evaluate that from -2 to 0. That's what I should have done. Silly me. So when we do this, we end up getting ln of e to the 0 minus 1. Hey, wait. I can't plug in 0 because then I get oof. So careful, right? So if we take the limit as x approaches 0, this is approaching something infinite. I mean, it still ends up being the same thing. This approaches something infinite, which is illegal. Since that limit doesn't exist, that's our problem. So I should have picked this one. It's not that the original function has a problem, it's that its integral has a problem. So the previous one, I think, is a good reminder for us, or like, was it the previous one? Shoot. I don't know. I don't see what I want to talk about. Yeah, I'm filming a video, but you can eat in here. All right, yeah, definitely. All right, so a little weird, but yeah, okay. Let's. I'll stop there and continue the paper in the next one. Yeah, let's do that.